Welcome to a deep dive into a really fascinating area of astronomy,
Oh, yes.
astrophotonics,
Yes.
and specifically
Right.
what it means for our search for extraterrestrial life.
Okay. Okay.
So
Yeah.
we're going to be looking at how this really cutting-edge technology
Yeah.
is really changing how we're able to not just detect Earth-like planets out there,
Right.
but
Uh,
analyze their atmospheres for signs of life.
yes.
Now, as astronomy fans, I know,
Right.
you guys already know,
Yeah.
the basics of exoplanet research.
Absolutely.
So we can jump right into the details.
Okay.
So
Yeah.
astrophotonics, at its core,
Uh-huh.
is basically the combination of photonics,
Right.
the science of light,
Yeah.
with astronomy.
Okay. Yeah.
So the
Okay.
question we're looking at today,
Mm.
how close are we to finding another Earth out there?
Right.
And
Right.
could astrophotonics be the key to doing that?
Well, the field of exoplanet research
Uh,
has really come a long way. I mean, we've moved beyond just discovering them.
Right. Sure.
You know, we have over 5,400 confirmed exoplanets
Wow.
as of August 2023.
Okay.
According to the Exoplanet Archive.
Gotcha.
And now we're moving into the area of characterization.
Okay.
So
Right.
now the focus is on understanding the atmospheres of these planets
Mm-hmm.
to see,
Okay.
how habitable they might be.
If you look at Figure 1 from your source material,
Okay.
it shows all the known exoplanets,
Uh-huh.
and it maps their mass against their orbital period.
Right.
You'll see
Yeah.
that terrestrial planets, like our Earth,
Uh-huh.
are still pretty rare to find.
Yeah.
And even fewer
Yeah.
are in what we call the habitable zone,
Right.
which is that sweet spot
Yeah.
around a star
Uh-huh.
where conditions might allow liquid water to exist.
Yes.
Remarkably, we still haven't found a true Earth-Sun analog.
We haven't, no.
Oh,
And techniques like the transit method
yeah.
and radial velocity
Yeah. Right.
have been good at finding exoplanets.
Yeah.
But it's the radial velocity method specifically
Okay.
that holds the most promise
Okay.
for finding planets that are really like Earth,
Gotcha.
orbiting stars that are similar to our sun,
Oh.
especially with the new Habitable Worlds Observatory coming up.
Right.
This technique needs extreme precision
Okay.
because it measures tiny changes in the velocity of starlight caused by a planet's gravity as it orbits.
So we're talking about
Body.
detecting velocity changes that are smaller than 50 centimeters per second.
That's right.
And even ideally,
Yeah.
down to 10 or 20 centimeters per second
Uh-huh.
over a period of half a year.
Yeah.
That's
Amazing.
like measuring the speed of a snail
Yeah.
crawling on a leaf from light years away
It's incredible.
to achieve this level of precision,
Yeah.
which is called extreme precision radial velocity,
Yes.
or
Yep.
EPRV. We need instruments with crazy stability and accuracy.
You need that.
And that's where astrophotonics comes in.
That's right.
It offers this powerful tool
Yeah.
called the laser frequency comb, or LFC.
Yes.
Now,
Mm-hmm.
an LFC isn't like a real comb made of light,
Right, right.
even though the name kind of makes you think that,
Mm-hmm.
right?
Yeah.
So think of an LFC as a ruler for light.
Okay.
It sends out a bunch of really stable,
Yeah.
evenly spaced laser lines,
Uh-huh.
and each line has a very precise frequency.
Right.
These lines basically act like a reference grid,
Yeah.
so astronomers can calibrate their instruments
Right.
super accurately,
Yeah.
and this makes sure that they stay stable
Mm-hmm.
for decades,
For a very long time.
which is really important for EPRV measurements.
Yes.
That can take many years.
That's right.
So an LFC is like a perfectly tuned tuning fork for light
Uh-huh.
that stays in tune for decades.
Yeah, that's a good analogy.
And it's this crazy precision and stability
Yeah.
that allows us to find those teeny tiny wobbles in
Right.
starlight
Mm-hmm.
that are caused by a planet like Earth.
Yes, exactly.
The source material talks about 3 ways to create these LFCs:
Yeah.
mode-locked lasers,
Uh-huh.
electro-optic combs,
Uh-huh.
and chip-based LFCs.
Yeah.
Can you tell us more about the differences?
Sure.
And why chip-based LFCs are so exciting for space missions in the future?
Well, mode-lock lasers were the first way to make LFCs,
Okay.
but they need extra filtering to get that precision. We need
Right.
electro-optic combs give us more control
Okay.
over the spacing between the comb lines,
Uh-huh.
but they can be tricky to actually build
Right.
chip-based LFCs.
Yeah.
They're still being developed,
Uh-huh.
but they have a lot of potential
Okay.
because they're so small
Right.
and because they can be integrated.
Gotcha.
They're the best bet for space missions.
Okay.
Like the Habitable Worlds Observatory, where size and toughness are really important.
Okay.
Yeah.
The source material also talks about something called spectral flattening
Right.
and how important it is
Uh-huh.
to make the LSC signal as strong as possible.
Yes.
So
Yeah.
why is this so important for getting that super high precision?
Well, the intensity of light
Okay.
across an LFC
Mhm.
can change.
Okay.
And this affects the signal-to-noise ratio,
Right.
and it can mess with the precision of the measurement.
Gotcha.
Spectral flattening basically smooths out the intensity
Okay.
across all the comb lines.
Okay.
So it optimizes the wavelength solution
Gotcha.
and makes the signal much clearer.
So it's like making sure that a radio transmission
Uh-huh.
is clear and consistent across all the channels.
Exactly.
This is especially important for EPRV
Yeah,
because we're dealing with signals that are super faint.
that's right.
Right.
Yeah, we need all the precision we can get.
Right.
And a big improvement has been moving from those big, expensive spectral flatteners
Right.
to compact on-chip ones.
Okay.
These on-chip flatteners,
Huh.
which use things like arrayed waveguide gratings or AWGs
Okay.
and Mach-Zehnder interferometers or MZIs. They're
Right.
smaller,
Uh-huh.
more stable,
Okay.
and they could even be more efficient.
This miniaturization
Yeah.
seems super important for future space missions,
Yeah,
where space and weight are really limited.
that's right.
right.
On-chip flatteners are a big step forward in making astrophotonic instruments
Okay.
more compact,
Ah,
tough,
Right.
and better suited
Right.
for the harsh environment of space.
Right.
So yeah,
Cool.
it's a big deal.
Awesome.
Yeah. Okay, so let's say we've found a planet that might be like Earth
Okay.
using EPRV.
Right.
The next big step is to look at its atmosphere
Uh-huh.
to see if there are any signs of life,
Okay.
what we call biosignatures.
So that brings us to spectroscopy, which is basically analyzing light
Right.
by splitting it into its different colors,
Uh-huh.
like a prism.
Yeah, think of a planet's atmosphere.
Okay.
It's like a special mix of gases,
Okay.
and each molecule absorbs and emits light
Okay.
at specific wavelengths.
So
So it creates a unique fingerprint.
right.
So by looking at the light
Yeah.
that passes through the atmosphere,
Uh-huh.
we can see what molecules are there,
Okay.
like water, oxygen,
right.
methane,
Gotcha.
and
That
others.
spectroscopy is
Yeah.
like reading the chemical fingerprint of a planet
That's a good way to put it.
and looking for clues that might mean there's life.
Exactly.
It's a super powerful tool,
It is.
but I imagine it also comes with some pretty big challenges.
Oh, absolutely. The challenges are huge.
Okay.
The light from the star
Yeah.
can be billions of times brighter
Wow.
than the light reflected from the planet.
Yeah.
It's like trying to hear someone whisper
Mhm.
at a rock concert.
How do astronomers deal with that crazy difference in brightness
Right.
to actually see the planet's light?
Well, we need really advanced
Okay.
high contrast imaging techniques
Uh-huh.
on big telescopes
Right.
to separate the planet's light
Okay.
from the glare of its star.
Right.
There are two main strategies.
Okay.
Wavefront sensing and control,
Gotcha.
and starlight suppression.
Let's start with wavefront sensing and control.
Okay.
How does that work?
So imagine a telescope mirror
Okay.
as this perfectly smooth surface,
Right.
but in reality,
Yeah.
no mirror is perfectly smooth.
Huh.
There are tiny imperfections in the mirror's shape,
Gotcha.
and there's turbulence in the Earth's atmosphere.
Right.
All of this distorts the starlight,
Mhm.
making the image blurry.
Okay.
Wavefront sensing measures these distortions,
Right.
and then we use something called a deformable mirror,
Okay.
which is a really cool piece of engineering
Yeah.
to correct those distortions in real time.
So it's like,
A tiny adjustable mirror
uh-huh.
that constantly changes shape.
To compensate for the messed up starlight.
Exactly. It's like active correction
Cool.
that makes the image much sharper,
Okay.
and it makes it easier to see that faint light from the planet.
What about starlight suppression?
Right.
How do we actually dim the star?
Well, that's where coronagraphs come in.
Okay.
They're these really sophisticated optical devices
Uh-huh.
that we put inside the telescope.
Okay.
They block out most of the starlight,
Gotcha.
creating a dark area around the star
Right.
where we can then see the much fainter planet.
So it's like
Yeah.
creating an artificial eclipse
Uh-huh.
inside the telescope.
Yeah. Good way to think about
So
it.
we can see those faint planets orbiting the star.
Exactly. But coronagraphs,
Okay.
they've revolutionized high contrast imaging,
Uh-huh.
but they still have their limits.
Okay.
To get the super high contrast we need,
Right.
to image Earth-like planets.
Uh-huh.
We need even more starlight suppression.
And that's where photonics comes in again.
Right back to the power of photonics.
Yeah, it offers a really remarkable solution.
The source material mentions 2 ways photonics can suppress starlight.
Uh-huh.
Photonic lantern wavefront sensing and control.
Okay.
And photonic nulling.
Yeah.
Can you explain those?
Sure. So let's start with photonic lantern wavefront sensing and control.
Okay.
Photonic lanterns are these tiny devices called waveguides.
Uh-huh.
They're basically microscopic channels
Okay.
etched onto a chip
Right.
that guide the light. And these lanterns can take multimode light, which is basically a jumbled mess of light waves,
Gotcha.
and convert it into single mode outputs,
Right.
creating these nice separated beams.
So a photonic lantern is like a traffic controller for light,
Mm-hmm.
organizing that chaotic starlight
Yeah.
into these well-behaved beams.
That's a good way to put it, and here's the important part.
Okay.
By looking at the distortions in these individual beams,
Uh-huh.
we can do wavefront sensing at the focal plane of the instrument.
Oh,
'Cause the
good.
light is focused.
Right.
This focal plane sensing is more precise because it gets rid of errors
Gotcha.
introduced by other parts of the system.
So photonic lantern wavefront sensing
Uh-huh.
is a big improvement
It is.
in terms of precision and accuracy.
Yeah. It lets us control the wavefront better,
Right.
leading to sharper images and better starlight suppression.
It sounds like it.
And you know what?
Go on.
This technology has already been tested
Oh, wow.
on the Subaru Chronographic Extreme Adaptive Optics Testbed,
Okay.
or SXAO,
Right.
at the Subaru Telescope in Hawaii.
Awesome.
And it worked.
That's impressive.
Yeah, we achieved closed-loop control
Okay.
of multiple Zernick modes,
Uh-huh.
which are basically mathematical descriptions of wavefront distortions.
And the source material also mentions a hybrid lantern.
Right.
What makes this hybrid approach even better?
Well, a hybrid lantern combines the best of both worlds. Right.
Multi-mode and single-mode operation.
Uh-huh.
So it could potentially improve contrast and stability even more.
It's amazing how researchers are always pushing the limits,
It really is.
refining and improving these techniques to get even better precision.
Exactly.
And then there's photonic nulling,
Right.
which sounds almost like magic.
It's pretty cool.
How does that work to suppress starlight?
So photonic nulling uses the idea of destructive interference.
Okay.
Imagine 2 waves of light
Uh-huh.
meeting crest to trough.
Okay.
They cancel each other out,
Right.
creating a dark spot.
Gotcha.
Photonic nullers use this principle to block out the starlight
Right.
while letting the faint light from the planet pass through.
So it's like creating a quiet zone
Yeah.
around the star, where we can hear those faint whispers of light
Uh-huh. That's a good analogy.
coming from the planet.
There are 2 main ways to do photonic nulling.
Okay.
GLINT and mode-selective photonic lanterns.
Let's start with GLINT.
What does it stand for?
It stands for Guided Light Interferometric Nulling Technology.
Okay.
It's a mouthful.
Yeah.
It involves splitting the telescope's pupil,
Okay.
which is basically the opening that collects the light,
Uh-huh.
and then routing the light
Right.
from each segment
Okay.
through this three-dimensional photonic chip.
Gotcha.
Inside the chip,
Uh-huh.
the light from the different segments
Okay.
interferes with each other in a
Okay.
very specific way
Okay.
to create a deep null,
Right.
canceling out the starlight.
It sounds super complex.
It is.
Routing and interfering light
Yeah.
within this microscopic chip.
It's pretty amazing technology.
What are the pros and cons of GLINT?
Well, one big advantage is that it can create very deep nulls,
Okay.
suppressing starlight by a lot.
Uh-huh.
But a big challenge is making those nulls achromatic,
Okay.
meaning that they work across a wide range of wavelengths.
Which is crucial, right?
Yes.
We need to look at a wide spectrum to capture the whole chemical fingerprint of the planet's atmosphere.
That's right.
Right.
Making achromatic nulls with GLINT.
Yeah.
It's just something we're still working on.
Yep.
And it's really important for making this technique work as well as it can.
What about mode-selective photonic lanterns?
Okay, so these lanterns offer a more passive way to do nulling.
Right.
They have this special ability to suppress starlight in certain output modes
Okay.
while letting the light from the planet pass through.
So it's like the lantern filters the light, blocking the starlight, but letting the planet's light shine through.
Yeah, good analogy.
Okay.
So while mode selective nulling might not be as strong as GLINT,
Right.
it's easier to do.
Uh-huh.
And it's still a really promising way to suppress starlight.
The source material mentions some promising results with mode-selective lanterns.
Yeah.
What kind of null depths have they achieved?
Well, in the lab, we've seen null depths of 10.3 to 10.2,
Okay.
which is already pretty good.
Uh-huh.
And with more research, especially in reducing crosstalk between the different modes,
Oh, yeah.
these lanterns could get even better,
Yeah.
maybe even as good as GLINT.
So it's a race between two promising approaches,
Yeah. It's exciting.
each with its own advantages and challenges.
Exactly.
And I imagine researchers are also trying to combine these techniques
Oh,
to
definitely.
get even better starlight suppression.
That's right. The field of astrophotonics is constantly moving.
Uh-huh.
People are always coming up with new ideas,
Right.
pushing the boundaries.
Yeah.
Combining different techniques is a powerful way to drive innovation.
It's fascinating
It is.
how photonics is giving us such elegant solutions
Uh-huh.
to these really challenging problems in astronomy.
Absolutely.
But we're not done yet, right?
Not quite.
We still need to analyze that faint light from the planet
Uh-huh.
to look for those biosignatures.
Yeah, that's right. And that's where photonic spectroscopy comes in.
Right.
And it's just as groundbreaking as the other techniques.
Awesome. Okay, so we've talked about how astrophotonics can find those really faint signals from exoplanets
Right.
and then isolate them.
Uh-huh.
But now comes the final challenge.
Yeah.
Actually analyzing that light
Right.
to figure out what secrets it holds.
To unlock the mysteries.
This is where photonic spectroscopy comes in.
Exactly. And photonic spectroscopy
Okay.
lets us look at the light from an exoplanet
Right.
and spread it out into a spectrum.
Right.
And this reveals those unique fingerprints
Oh.
of the different molecules
Yeah.
that are in its atmosphere.
So it's like using a really high precision prism
Yeah.
to break down the planet's light into its different colors.
Uh-huh.
And each color tells us about specific molecules.
Right. And for this, we use a technology called arrayed waveguide gratings,
Okay.
or AWGs.
Gotcha.
These are tiny devices
Yeah.
etched onto a chip,
Ah.
and they act like super precise prisms,
Okay.
splitting the light
Right.
really efficiently
Yeah.
and really stable.
So it's like
Yeah.
a miniature, super precise spectrometer
Exactly.
able to analyze those faintest whispers of light
Uh-huh.
from these distant worlds.
That's right. And because they're so small
Okay.
and stable,
Uh-huh.
and they don't have any moving parts,
Right.
AWGs are perfect for space missions,
Makes sense.
where reliability is super important.
Okay.
Yeah.
Now, the source material mentions that adapting AWGs
Mm-hmm.
for exoplanet characterization
Yeah.
has some unique challenges.
It does.
What are those?
So current AWGs,
Okay.
they're designed for high-resolution spectroscopy,
Uh-huh.
but for exoplanet work,
Yeah.
we need lower resolution,
Okay.
meaning we need to be able to see broader spectral features.
One that's better at seeing the bigger picture
Yeah.
of the planet's chemical fingerprint.
Right, not just the fine details.
Okay.
And, researchers are making good progress
Uh-huh.
developing these specialized AWGs,
Awesome.
new advancements
Right?
in silicon nitride and silica platforms
Right.
have shown really impressive efficiency,
Uh-huh.
like over 70% in some cases.
Wow.
This means that over 70% of the photons from the planet
Right.
are captured and analyzed,
Wow.
which makes the instrument much more sensitive.
It's great to see this progress.
Yeah, it is.
It's paving the way for future missions,
Uh-huh.
like the Habitable Worlds Observatory,
Right.
to carry these compact and powerful photonic spectrographs
Yes.
that can actually detect these tiny clues of life
Mhm.
on faraway planets.
It's really exciting.
It is.
So all these advanced technologies coming together,
Yeah.
EPRV for finding the planets,
Uh-huh.
wavefront sensing, and photonic nulling for
Right.
blocking the starlight,
Right.
and photonic spectroscopy
Yeah.
for looking at the atmosphere. It's really changing how we study exoplanets.
Looking at figure 2
Okay.
from your source material,
Yeah,
we can see two potential instrument architectures
right.
that combine all these technologies. Can you walk us through them?
Sure. So the top part of figure 2
Okay.
shows a setup where you have a coronagraph first,
Uh-huh.
then a mode-selective lantern nuller,
Okay.
then a beam combiner
Right.
that's optimized for something called kernel nulling,
Gotcha.
and finally the AWGs for spectroscopy.
So it's like a multi-step process where
Yeah.
each step refines the light even more until we finally get that faint signal from the planet.
Exactly. And then the bottom part of figure 2
Okay.
shows a setup where you have a coronagraph
Uh-huh.
followed by a GLINT-like nuller
Right.
in the pupil plane.
Okay.
And then again, the AWGs for spectroscopy.
Both architectures seem to use a coronagraph
Uh-huh.
and some kind of photonic nulling to get rid of that starlight.
Yeah,
So how do we decide which one to use?
that's a great question.
Yeah.
And researchers are trying to figure out
Uh,
the best combination of technologies
okay.
for different mission needs.
Gotcha.
So we have to think about things like
Uh-huh.
how much contrast we need,
Right.
the range of wavelengths we want to look at,
Okay.
how complex the system is,
Yeah.
and how mature the different technologies are.
The source material also mentions using things like masks
Right.
and phase plates
Uh-huh.
along with photonics.
Yeah.
How do those fit in?
So masks and phase plates
Okay.
are basically extra optical tools
Gotcha.
that we can use
Wow.
to shape and control the light even more.
Okay.
This helps us make the starlight suppression
Right.
even better.
So they can be used with both coronagraphs and photonic nullers
Uh-huh.
to create even deeper nulls
Exactly.
and improve contrast.
It's like having a whole toolbox
Yeah.
of specialized tools to tackle starlight suppression.
And then there's predispersion, which
Yeah.
we talked about earlier,
Mhm.
splitting the light
Yeah.
into different spectral channels
Okay.
before combining the beams.
Uh-huh.
That's another way to get broader nulls, right?
Yeah, predispersion helps us do more targeted nulling
Fair.
in each channel,
Okay.
so we can block out starlight more effectively
Gotcha.
across the whole range of wavelengths.
Okay.
But it does make the system more complex,
Right.
and we need to be really careful with calibration
Uh-huh.
to make sure we're getting accurate measurements.
So designing these instruments
Yeah.
sounds like a delicate balancing act.
It is. We're trying to get the best performance while keeping things manageable
Right.
and making sure everything works reliably.
Especially for those long space missions.
Exactly. Those are tough environments.
The source material points out some key challenges
Yeah.
for future research. What are those?
So one big challenge is figuring out
Okay.
which type of coronagraph works best
All right.
with photonic nullers.
Okay.
Different coronagraphs
Right.
have different pros and cons,
Yeah.
and we need to see
Yeah.
how well they work with specific photonic nulling techniques.
Okay.
Another challenge is understanding how the different photonic nulling options
Uh-huh.
behave across different wavelengths
Right.
and whether predispersion is actually doable
Okay.
in a real system.
And lastly,
Yeah.
we need to figure out
Mm-hmm.
how to control and calibrate these super sensitive photonic components.
Right. We need to make sure they stay stable and accurate over long periods of time,
Yeah.
especially when we're working with very few photons,
Oh, right.
which is typical for exoplanet observations.
It sounds like we're at the beginning of
Yeah.
a whole new era in exoplanet research
Uh-huh.
where astrophotonics,
Yeah.
with its incredible precision and flexibility,
Mm.
will let us see into the atmospheres of
Yeah.
these distant worlds and search for signs of life
Absolutely. It's amazing.
like never before.
Yeah. I'm really excited about the future.
Oh, too.
Astrophotonics is a field that's changing so fast,
Uh-huh.
and it has so much potential.
It really does.
As we keep improving these technologies
Right.
and coming up with new innovations, we're
Mhm.
getting closer and closer
Yeah.
to answering that big question.
That age-old question.
Yeah. Are we alone in the universe?
It's such a big question.
It is.
And it's incredible
Huh.
how photonics is playing such a key role in our search for the answer.
It's a privilege to be part of it.
Thanks for joining us on this deep dive
My pleasure.
into the world of astrophotonics
Yeah.
and what it means for finding life beyond Earth.
That's been great.
If you want to learn more,
Mm-hmm.
check out the 2023 Astrophotonics Roadmap
Okay.
mentioned in your source material.
Yes. Definitely a good read.
It gives a great overview
Uh-huh.
of this amazing and rapidly developing field.
It's a roadmap to a future.
Yeah.
Full of incredible discoveries.
It really is.
And I have no doubt
Mm.
that astrophotonics will be leading the way.
It's an exciting time to be an astronomer.
It is.
That's for sure.
Absolutely.